and the result. So you please go ahead.
Yes, thanks, Sarge, and everyone. It's a really great pleasure for me to talk here. So my talk title is High-Order Proton Cumulants in Google Collisions at 3 GeV from Starfish Target Experiment. Here's my outline. So after the motivation, I'll show the analysis details, which includes particle identification and several analysis methods. In the result part, I will show the new 3 GeV measurements, as well as the analysis from the BS1 data. Then it is a summary and outlook. So motivation part. So one important thing in high-ion physics is to explore the RHIC structure of the QCD phase diagram. So the phase diagram is displayed in terms of temperature and baryon chemical potential. So there are two phases in this diagram. One is the hydronic phase, while the other is the quark-gluon plasma phase. About the phase transition about these two phases, it is well known that at 0 μb, it is a smooth crossover. While at large μb, models and series calculation predict a first-order phase transition line, as well as a critical endpoint of the first-order phase transition boundary. So many experiments are conducted at different energies, so that can be used to scan the phase diagram at different μb to search for a critical point and the first-order phase transition line. This slide shows my observable, the high-order cumulant. So it is proposed that the high-order cumulant are permitting observable to trace the phase transition boundary and study the critical phenomena in QCD. There are mainly 2 points about why the high-order cumulant are sensitive. The first point is the high-order cumulant are sensitive quantities to the correlation length of the system. As you know that the correlation length in the vicinity of critical region will increase, and the high order larger than 2 are sensitive to a larger higher order of the correlation length. The second point is the higher cumulants can be directly related to the susceptibility of the system. They have a direct comparison with model calculations. In the left bottom, I show the cumulative definitions up to 4th order, C1 to C4, and several cumulative ratios, skewness, kurtosis, and C2 or C1 and C3, C4. In experiment, we usually use these 2 skewness sigma and kurtosis sigma square in experiment. And on the right-hand side is a plot about the property about skewness and kurtosis. Yeah. So this slide I shows the star BS1 analysis from for the net proton cumulant. So on the left-hand side, there are 2 plots. It's a prediction from model side. So from model calculation, it predicts that due to the contribution from critical point, the kappa sigma square will show a non-monotonic energy dependence. But the calculation from Poisson fluctuation or canonical ensemble, the kappa sigma square is unity. So on the right-hand side is the net proton cumulant measurements from the star BS1 Google collision data from 7.7 to 200 GeV. The most central 5% result for kappa sigma square is displayed in the red markers. As you can see, there's a non-monotonic energy dependence with 3.1 sigma significance. But you can also see below 20 GeV, there's still large statistical error bar. The BS2 analysis, we hope, will shrink the error bar and confirm this non-monotonic chain. So our new measurement at 3 GeV will fill this gap of the energy dependence chain. The analysis detail part. This is the star detector system. So in our fluctuation analysis, we mainly use 2 detectors. One is TPC, which is to identify TPC and a TOF detector, which are used to identify protons and their flighting time. Then the next slide is a setup of Starfish target experiment. This is a profile of the whole detector. This region is a TPC detector, and the goal target is its gold foil, about 25 micrometer thick. It is placed at the entrance of a TPC detector. So one important point for Fish target experiment, it can extend the coverage of baryon camp potential up to 750 MeV. In the analysis, about 140 million data are used that were recorded in the year of 2018.
I'm so sorry. Can you stop your iPhone alarm when you're back?
Oh, sorry. This is particle identification that using TPC and TOF. The left panel are energy loss versus rigidity, and this band is proton. And the red line is a theoretical prediction from the base block model. And the middle plot is TOF PID. The y-axis is TPC PID and versus TOF square. The red dashed box indicates a cut we use to select proton. So with these 2 detectors, we ensure the proton purity is about 90.6% of all regions of our analysis window. With these 2 PID detector PID, we can select proton. The right-hand side plot is PT versus proton rapidity. The rapidity is shifted to center of mass frame. So the red dashed box is the analysis window from -1 to 0, and you see the clear difference around in this plot. It is due to the TOF PID. We apply the TOF PID for a momentum larger than 2 GeV. The momentum is in lab frame. Yeah, from the current data of 2018, only half meter rapidity are covered in current data. This is centrality determination. We are still using the charged particle multiplicity from the TPC full TPC acceptance to define centrality. The left-hand side plot is the reference multiplicity of different type. The data are shown as black circles, and we are using Monte Carlo global model to fit the data and to define different centrality class. And the black marker
I don't hear him.
Yes.
The same here.
Where he's coming from, maybe there's sometimes the internet there is not very stable, probably.
He's at CCNU now.
Yeah.
Okay, let me call him. Maybe he has some internet problem. Let me.
Can you hear us? We don't hear you.
Yeah, it looks like he's continuing his lecture.
That's right. Can you switch to your phone hotspot? Wi-Fi is not stable. You
Tell him that he has to go to, icon here in the bottom and choose the phone to do it. I don't know whether he knows.
know.
He knows? Okay.
I think so, yeah.
Sorry,
Well,
can you hear?
Yeah, we can hear you now. Yes.
Okay, thank you.
Yeah, you were stuck here. Maybe yeah, you can on this slide.
Maybe you can turn your video off. That will conserve some bandwidth.
Yes. You could turn
Maybe
your video.
everybody will turn the video off.
Yeah.
that
The show-
doesn't make much difference on Zoom. Zoom's very efficient. It's
Unless it is from China, Jim.
Can you use your phone's hotspot?
Yeah, I'm using my phone hotspot.
Okay, that should be fine. Yeah, go ahead.
Okay, so yeah, I'll start here briefly. Show this slide.
You can go from next slide. This was fine.
Okay, sure. Yeah. So the centrality. We use the reference multiplicity to define centrality and use a global model to fit data and define the centrality of different class. And the blue and the dashed lines are for pileup correction, which I will show in later slides. And so then with when the centrality class defined, we can plot the proton multiplicity distribution as shown in the right bottom plot, which is for different centrality, 5% there to 40, and the most preferred centrality we can obtain in current data. The acceptance cut are from -0.5 to 0, and with the PT from 0.4 to 2 GeV for this 3 proton distribution. The analysis method, I will show mainly 2 methods. One is the detector efficiency correction on cumulants. The second one is the pileup correction for the initial volume fluctuation. Yeah, the detector efficiency correction. So in this 3 GeV analysis, we are using a track-by-track efficiency correction method. So in the BS1 analysis, the conventional method, we're using a 2 efficiency beam method. So with this new method applied, we can handle infinite efficiency beams. So for example, if you can see the middle plot, which is efficiency as a function of PT versus the pseudo PT. The left-hand side is TPC.
Tak, oczywiście, wszystko dobrze.
Yeah, the left-hand side is the TPC tracking efficiency, and the right-hand side is the top matching efficiency. As you can see, the efficiency is not uniform, and on the right-hand side you see there are gaps in the efficiency map. So this track-by-track method is necessary to handle the infinite efficiency beams for precise measurement. The second point is this efficiency correction method can reduce calculation time. The CPU time is tested in the paper. The CPU time will not grow with the number of efficiency beams. So the PT and the rapidity dependence efficiency are used in our analysis. The next slide is the pileup correction. So there are several types of pileup events. Some are related to the beam and the experimental issue. And we are correcting one type of pileup event in this 3 GeV analysis. They are from the single collision. They occurs in a very small time interval. So then the detector cannot distinguish them. So in this analysis, we used an analytical method to directly correct cumulant. It has an assumption that the pileup events are independent, a combination of single collision events. So, and this method in only one input, let's see, the pileup fraction, or we call it pileup probability, which is assigned alpha. So the alpha is important for the precise measurement, for precise correction. So we are using a folding approach to determine the pileup fraction. The method can be briefly shown in this formula. The P means probability distribution, and M is measured. The measured probability distribution can be a sum of the true single collision distribution and the pileup probability distribution. If we know the pileup fraction from Monte Carlo simulation or somehow, we can analytically solve the true, or we say single collision distribution. That's the method. And on the bottom is the simulation. It's a simulation with the alpha equals pi 0.5. The blue lines and the red lines are single collision distribution and the pileup distribution. You see the right top plot is the alpha, the pileup fraction as a function of different reference multiplicity. The fractions are largest at central collisions. The right-hand side is the single collision multiplicity, a correlation plot of a single multiplicity. So the point, the density means weight. We can extract this weight and determine the pileup probability distribution. So we validate this pileup method on UrQMD model. The right top plot is the reference multiplicity from UrQMD model. We randomly combine two events in UrQMD and construct the pileup events. The black circles are pileup UrQMD, which include the single collision events and the pileup events. And the raw UrQMD is the pure UrQMD data. And we firstly try the global fit to pileup UrQMD data to extract the pileup fraction. Then we try to apply this method. So on the right-hand side is the application of the pileup correction method on cumulants. The cumulants are shown for C1 to C4 and the ratios up to fourth order. The x-axis is pileup probability or pileup fraction, the alpha, and the y-axis is cumulant and ratios. The black circles are the raw UrQMD calculation from the red squares. So it is the true value we see here, and the calculation of cumulants from the pileup UrQMD are shown as the black squares. We see that the pileup effect enhances the cumulant and the ratios. And there are two tests on the correction method. One is the closure test using the single collision distribution directly from our simulation. And we see that up to 10%, the pileup correction can effectively finish its job, can do this job. And the global method we used to extract probability, which looks do not perfectly done the job, which is mainly due to the imperfect fit of the global fit to data. So in the next slide, I show the unfolding approach. Let's first see the bottom plot, the data and the unfolded single collision distribution. We see that the single collision distribution perfectly fit the data at a lower multiplicity and abstract the single collision distribution as well as a pileup fraction. Then we use this single collision distribution to apply this pileup correction on cumulant. On the top plot is cumulant ratios as a function of different essentiality. The most central 5% is shown as 0. The more peripheral means the integer goes larger, means the more peripheral essentiality. And still the black circles are raw UrQMD calculation, and the square is calculation with pileup events. And the red stars are the pileup corrected cumulant using the unfolded single collision input. We see that with this method, the unfolded results are consistent with the closure test, consistent with the true result, we show as the black circles. We apply this correction on data. The cumulant up to fourth order as a function of different essentiality. The M part, the most essential collision are around 300 for M part, and the peripheral is the most peripheral is the 50 to 60, and the cumulative without pileup correction is shown as black at the open circles, and with pileup, the pileup corrected cumulant are shown at the black star. The input are from the unfolding approach. From the directly comparison of these two results, we see that the pileup effect only shows this difference only for the most essential essentiality. The most essential essentiality are affected by the pileup events. And this slide shows the initial volume fluctuation correction. So we know that we are using a reference multiplicity to define essentiality, because it has a correspondence to the initial geometry of a collision. The collision volume is not a well-defined quantity. So here we relate it to the number of participants, or we call it wooden nuclear within wooden nuclear model. We use a UrQMD simulation. The left top plot is the simulation, the reference multiplicity versus the number of participating nucleons. We see that for fixed reference multiplicity, the impart width covers a larger range. This additional volume fluctuation will this is wanted in our fluctuation measurement for our observable. At the right-hand side plot is impart width. It is the impart RMS of a different impart distribution for fixed reference multiplicity. And the y-axis is reference multiplicity. You see that for most central collision or most peripheral collisions, the impart width is smaller, and it is the largest for a multi-central collision, around 20 to 30%. So this volume fluctuation effect are need to take care in the fluctuation measurement. We are from this reference. We use this volume fluctuation correction on data. We tested this method on data. The method had a few assumptions. The most important assumption is it assumes that the particle production is independent combination of from different sources. Here the sources participating nucleons. So then we can construct our moment generation function. Here, as you can see here, the left-hand side is it's a moment generating function of from all sources, and it can be a product of the generated function from different cells. And to solve this function, we have the cumulant. The kappa here means cumulant. We use a capital C for cumulant, and here it's the kappa. And the left hand side, the kappa, the cumulant are the measured cumulant, and the right hand side cumulant are combination of fluctuation volume and the true fluctuation that without fluctuation from volume. That's what we wanted. Then we can solve these formulas and extract the true true cumulant we want. And this method needs besides the assumptions, it needs the input. The input that it need most is the impart distribution. So which we don't know from data. We have to rely on models. So the on right hand side is the impart distribution from two simulation. One is a global simulation, and the other is the UrQMD simulation. We see that there are difference from these two models. So that will bring different correction effect on the correction. So this method is model dependent. It depends on the impart input. So here the slide, we apply the initial volume correction on data using two different inputs. One is global and the other is UrQMD model. The plot shows cumulative ratios up to fourth order for the function of centrality. The black squares are data without the volume correction, and the blue triangles and the red circles are volume corrected results. From the comparison of these two corrected results, we see for third order and the fourth order ratios, the most central centrality are least affected by the volume correction, and the most central centrality are not so affected by the correction compared to the most peripheral and the most central centrality, but still it's model dependent. We do not want to. It's still need more knowledge about how we apply this method on data. And now it's the result part. I'll show the 3 measurement for centrality dependence, acceptance dependence, as well as energy dependence, which combines the net proton result from the BS1 and from the BS1 measurement. So here is the centrality dependence. The cumulative ratios are the function of different centrality. The data are shown as black squares. They are corrected for detector efficiency and the pileup effect. The volume fluctuation effect is not considered here. And the yellow line are calculation from UrQMD model. The acceptance cards are taken same with data, which is minus 0.5 to 0 and the PT from 0.4 to 2 GeV, which are same for both data and the UrQMD calculation. From a direct comparison of data and the UrQMD calculation, we see that the UrQMD model qualitatively reproduced the data's chain, and especially for C4 over C2 for the most central centrality. Then I show you the acceptance dependence plot. The cumulative ratios as a function of a different acceptance window. The left 3 panels are for the rapidity scan, rapidity minus 0.2 to 0, and we gradually increase the rapidity window up to the minus 0.5 to 0. And the right hand side is the PT's window scan. The PT from 0.4 to 0.8, 1.2 up to 2.0. And the data from 5%, most essential 5% are shown as black square, and the peripheral centrality are shown as the blue triangles. And the UrQMD calculation with same acceptance cuts are shown as the yellow line for central and the blue lines for peripheral. And still, from the comparison of data and the UrQMD calculation, we see the UrQMD model qualitatively reproduces data's trend. And it's expected for the smallest acceptance window. The cumulative ratios are reduced to the Proton statistics. This slide shows the systematic uncertainty analysis for our measurement. We have a few sources we considered. The first is essentiality. We changed the definition. We vary the essentiality definition by 1, and the pipe fraction, which is from the unfolding approach. And we also consider the track quality cut and consider the Proton purity. We vary the TBC and the TOF PID cuts and the efficiency value. The bottom plot are the contribution to the 3 different ratios. The values are shown as the first row, and the systematic contribution are shown in bottom. The largest contribution to the cumulative ratios are from DCE variation. Then this is my last plot, the energy dependence results. Here I show in the previous slide. This is the BS1 measurement for net proton cumulant and the proton cumulant. The acceptance, the energy is from 7.7 up to 200 GeV. And the results are only most essential 5% centrality. The acceptance is 4 meter repetitive minus plus 5. And the PT window are same with us. Here our new measurements are shown as the sine square. And besides the 3G measurement is the UrQMD calculation with same acceptance from -0.5 to 0. And the right hand side, the left hand side is Haley's calculation with the acceptance, the rapidity minus with rapidity minus plus 0.4. So we see you can see our new measurements are around -1, which is consistent with the UrQMD calculation with same acceptance. So we have a few conclusions from the new measurement. So the suppression from the Poisson baseline of C4 with C2 is consistent with the fluctuation driven by the baryon number conservation. And the consistency also indicates hadronate dominant region for the top 5% Gogo collisions at this energy. And we conclude that the QCD critical point, if discovered in the heavy ion collision, it could only exist at energy larger than 3 GeV. Then it is my summary. So in this analysis, we performed the systematic analysis for the 3 GeV Gogo collision data. And we report a C4 over C2 for this value, -0.85, and statistical and systematic error for the most essential 5% centrality with this analysis window. There are listed here 2 conclusions here. The consistency of the C4 over C2 with fluctuation driven by the baryon number conservation implies a hadronic dominant region at this 3 GeV, most essential 5% Google collisions, and the QCD critical point, if created in the ion collisions, could only exist at a higher energy other than 3. So besides the 3 GeV measurement, I'd like to show an outlook of the net proton cumulant analysis in the future BS2 data. So you know the BS2 have finished the data collection for energy from 3 to up to 20 GeV. The statistics compared to BS1 are 10 to 20 times larger. And we have several detector upgrade, the TPC, NTAP12, and APD detector. The benefit from the upgrade, we have better energy loss resolution and larger repeated coverage. We hope this future data analysis will confirm will shrink the error bar below 20 GeV and confirm the non-monotonic energy dependence chain. This slide I shows the abstract of our short paper. The title is Measurement of Proton High Order Cumulants in 3 GeV Google collisions and Implications of Further QCD Critical Point. Here the abstract. Then that's all for my slides. Thank you.
Thank you for this nice results and talk. Are there any questions for you?
Could you go back to the abstract so I could read it?
Yeah.
Thanks. And then other questions, please go ahead.
Volodymyr, you have a question, please go ahead.
Yes, hi, you. Thanks for the talk. Yeah, I have a question related to your conclusion that C4 over C2 is driven by baryon number conservation. And the question is that, well, it seems that C4 over C2 may be driven by baryon conservation, but C2 over C1 clearly is not driven by baryon conservation because you measured enhancement of the variance and not the suppression. And I wonder if you can comment on that.
Yeah, C2 or C1. Sorry, can you repeat your question? I will disrupt. Yeah, disrupted.
Yeah, my question is how to understand C2 over C1 being above unity, but at the same time C4 over C2 being driven by baryon number conservation, because we know that if C2 over C1 was also driven by baryon number conservation, then it would be below unity, not above unity.
Yeah, I'm thinking there's there's still the uncorrected volume correction or volume fluctuation. Yeah, for the C2 or C1, that is relatively larger for C2 or C1.
Okay, but then so that means that volume fluctuations are larger for C2 over C1, but they are smaller for C4 over C2 compared to baryon number conservation. Or you think that this might be an explanation, rather?
Yeah.
Okay. Okay, thank you. But I think this is, for me, it's still an open question, so I would be happy to explore this more. Mm-hmm.
Okay. Yu Zhang, maybe you have some plot on this or not? On the volume fluctuation correction contribution to different issues.
Yeah, you mean this part?
Yeah, maybe this helps, right? You can see that the contribution is more for C4 over C2 in the central collisions.
Well, the scales are a little bit different, but yeah, I see a large, I think it's -1 or yeah, for C4 over C2. And for C2 over C1, it's 0.1 or 0.2. Yeah, I think the scales make it a little bit more difficult. Well, maybe related to this, it's slightly different. So you're showing UrQMD with volume fluctuations. I assume this means that you varied the impact parameter of UrQMD simulations. Do you have also the result if you, for example, fix impact parameter in UrQMD to a constant value and see how it compares to?
Yeah, we did this kind of calculation. We restrict the impact parameter less than 3 and calculate the cumulant. And it shows me the result of, for example, C2 or C4 over C2 is change to close to 0. Yeah, slightly negative, slightly positive.
Okay, thank you. I mean, it would be interesting to see this side by side, but because I think this sort of separates the effect of volume fluctuation with and without including this impact parameter fluctuation. Okay.
Yeah. Thank you.
No, you have a comment or question?
My question is actually to Volodya. So you say that if it's a conservation, C2 over C1 should be less than unity. That's from a thermal model calculation. Is that right?
Yeah. If the only effect we include is baryon number conservation, it doesn't have to be thermal model. You can just throw particles and then apply some binomial acceptance. For example, you can also do this toy model. Then yes, you would always get less than unity if it's the only effect.
Right. As you can see that the transport model is above 1. So
yeah, that means that baryon conservation is not the only effect and it does not drive the behavior of C2 over C1. But I want to understand why it drives C4 over C2, but not C2 over C1. I
think it's more like your argument is based on thermal model. Because to me, at this energy, UrQMD is pretty good, almost for everything except the strangeness production. So it is above 1. So it's
Yeah, but it's not just thermal model. Like if you include baryon conservation as the only source of correlations, you don't have to assume that the system is thermalized. If it's the only effect which produces correlations between particles, then it will suppress C2 over C1. In thermal model or not, these are details. Yeah, but UrQMD has more like fluctuations of the number of participants, I guess, maybe even something else. So it gives different result.
Thank you.
Okay. Agnieszka, do you have a question?
Hi, great talk. So I have 2 questions. First question is, you say you compared with UrQMD, and I would like you to specify whether you had potentials included or not in your calculations.
So I included the efficiency correction, the pileup correction on data.
No, sorry, you may be misheard. When you compare with UrQMD simulations, do you use potentials in those simulations? Are there,
No, only the cascade mode. No.
I see, okay. Yeah, sure. Thanks. Okay. And the second question is, in one of your last slides, you show this C4 over C2, and you show that the result that you get from STAR is pretty similar to what Hades gets at even lower energy. But now if you compare C3 over C2, what you get is significantly different than what Hades gets, because STAR gets, I think, 0.9 something, and Hades gets about -2, depending whether they're correct for volume or not. So do you have a comment on that?
Actually, they somehow modified the volume correction and apply that. And for our analysis, due to the lack of the M-part knowledge, we don't apply this for now. So
I mean, yeah, but I think I would be very surprised because, yeah, go on.
What he meant to say is star is correct.
Sure, but you mean even in C3 over C2, where the difference is really, really big?
I know, but it's very strange, right? That not a data point from Hadis. It's very, very strange. I think C4 over C2 just happened they are close. Otherwise, I think
so.
To me, yes.
I mean, yeah, I am willing to accept that, you know, star might be correct, but I'm wondering like how, whether you performed any further tests, like how did you convince yourself that it has to be you that is correct and not Hadis people?
How do we convince ourselves it's correct? That's a good question.
Yes. Oh, okay.
Yeah. The Hadis number, for example, this data point already changed by a factor of 2 from 3 something dropped down there. Yeah, so Hadis has trouble. Star TBC is really good. Hadis has trouble in the sense as some crosstalks, so their correction is much, much bigger. Yeah. And yeah, I have much strong confidence on star data. In addition, we have 2 billion events we will analyze. Again, we will shrink this error by a little bit. So, yeah.
Also, the acceptance is not exactly the same between Hadis and star. Yeah, and maybe to the same topic, there is C2 over C1, which are quite different and which usually have even smaller error bars, so one can make stronger conclusions. Yeah.
I think acceptance difference here is relatively small, let's say. Yeah. For example, UrQMD, if we take a plus minus half unit, you're following this gold band, it goes to -4.
Yes.
Okay, but from Hadis, I think the difference between us is 0.8 basically versus 0.5. So. But that data point is very strange to me. It's too big. It's a positive and too large.
I see.
Yeah, of course, my friend in Hadis, they do not agree. But the question how to answer whether how do they believe their data is right, it's difficult to answer.
Is it, sorry, maybe I'm like taking over the entire bandwidth for questions, but is it even possible, given that detectors are different, could you somehow change your analysis to reproduce, if you think that what they do is incorrect, could you somehow do analysis in a similar way that they do and reproduce their error?
Yes.
Or
yes, we cannot go to their energy, but we can go into that acceptance with new data. Our current data, we cannot go to positive rapidity because of new detector was not used. For next set of data, yes, we can go to exactly the acceptance. We will show that. Yeah.
I see. Okay. Yeah, I'm looking forward to it. Thank you.
If we follow this, our mind a little bit set, we think go to lower energy, the baryon conservation effect is much stronger. This data point should go to more towards negative. Okay, that at least that's what our understanding. So I believe even we go to data acceptance, we will do in roughly a year from now with this exact acceptance. We will show that, yes.
I see. Thank you.
Thank you. Any other questions for you, son? Okay, if not, again, Yu Zhang for the nice talk, and thanks everyone for joining in the discussions. Yeah, so that's all for today. We'll see you next week. Yeah, for the HIT seminar. Okay, thank you. Bye.